Welcome back, everybody. This is the last conceptual video for the circuits lecture series. We're going to start off by talking about power, and then we're going to kind of pivot and go over to resistors and equivalent resistance, the notion of equivalent resistance. So let's just jump right in. Okay, let's talk first about power. So what is power? A reminder, power is energy per time. We're going to use nice light blue today. Energy per time. It lets me know how much energy is being absorbed or put out by a device. So if you've got a 1500 watt space heater, that means that your space heater is using 1500 joules every second. 1500 joules of energy every second. So in the context of electrical circuits, we usually talk about power produced by a battery or power dissipated by a resistor. So there are multiple different ways to write it. So power in an electrical circuit can be discussed as either energy per charge times charge per time. That still gives me energy per time, right? And this is a voltage or a change in voltage times a current. So that yields you the power of a battery, say. So battery power is going to be just the battery voltage times the current coming out of that battery. So I'll call this I total. It's the current coming out of that battery. Another way to talk about power is by applying our knowledge of resistors. So this is called Ohm's law. Delta V resistor is just negative IR. We can apply Ohm's law, this guy right here, to our fundamental understanding of power to find that, for example, the power dissipated by a resistor, is, again, delta V times I, which for a resistor, I can rewrite that delta V as IR. I'll keep the negative in for now, and then I'll explain why I drop it here in a sec. Which is just negative I squared R. So the negative sign right here basically just tells me that I'm losing the energy. The power is leaving the resistor. So I'm just going to drop it because I already know that. I squared R. The power dissipated by a resistor, the magnitude of it is I squared R. That's another way to talk about power. Finally, if I kind of do the reverse of what I did just now with Ohm's law, substituting it in, I can also write power dissipated by a resistor as delta V resistor squared divided by R. Okay, so what's the point of having all these different versions? If I have any two of voltage, resistance, and current, I can always calculate the power directly. I don't have to go through the motions of calculating the other one. So say I knew voltage and resistance. Well, then I can use this one. Say I knew only current and resistance, but not voltage. I can use this one. Okay, and if I knew voltage and current only, I could use this one. All right. I want to talk, pivoting a little bit now over to equivalent resistance. So there are two basic scenarios I want to talk about. First of all, what do I mean when I say equivalent? When I say equivalent resistance, I mean drawing the same current from a voltage source, or like appearing the same to a voltage source. So if I had a battery and it had two resistors in line, what would the equivalent resistance of these two resistors be? Okay, it would be whatever resistance the battery thinks it sees in the simplest possible circuit. So this is the equivalent resistance of these two resistors, R1 and R2, for the same battery. Okay, so for two resistors, if I want to reduce two resistors essentially to a single resistor, to understand the total resistance, the equivalent resistance of those two resistors, in series like this, when they're connected head to tail, that's what series means, when they're connected head to tail like this, the equivalent resistance of two resistors is R1 plus R2. And in general, if I've got like three resistors in series, say I've got R1, R2, R3, R4, the equivalent resistance of any number of resistors that are strictly in a straight line with each other like this is just the sum of them all together. To tie this back to Bernoulli equation / fluid stuff, it's as though I were connecting a bunch of rusty pipes. A bunch of rusty pipes connected head to tail are going to be more resistant than a single rusty pipe, like a single small rough section. Cool. Another way that I think of it is basically that each resistor presents kind of like an increase in difficulty for charge to flow. So if I stack them all up next to each other, I'm just making it harder and harder for the charge to make it through. Okay. The other one to talk about is parallel resistors. So resistors in parallel, the simplest parallel resistors look like this. I've got my battery again, and then I've got a branch. So the branch is key. R1 and R2. These are called in parallel. Notice that they aren't connected head to tail, they're connected tail to tail and head to head. That's what I mean by parallel. So parallel, compare this a little bit with series. Series is head to tail. The left side of my second resistor is attached to the right side of my first resistor. Whereas here, the left side of my first resistor is attached to the left side of my second resistor, and the same for the right. Both right sides are attached. Okay, so the equivalent resistance, the resistance that the power source would think it was dealing with if it was a single resistor, are equivalent. Are equivalent here for a parallel set of resistors is, it's kind of complicated, get ready. It's the inverse of the resistances summed, R1 plus R2, and then the inverse of that. So that's the equivalent resistance. Another way people write this, because this form is a little bit hard to remember, is just remembering to invert everything. So it's like the series version, except for that I invert everything piecewise. So 1 over R equivalent equals 1 over R1 plus 1 over R2. Now, one thing to avoid here, one thing that I see all too often is you forget about splitting up this fraction. So 1 over R equivalent for a series is not equal to 1 over R1 plus R2. Okay? That's not right. You have to split it up. So there's still two separate terms, 1 over R1 plus 1 over R2. Now, one interesting quality about this setup is that the equivalent resistance in parallel is always less than either R1 or R2. And it's also less than R2. So the equivalent resistance always decreases in parallel. You can put things in parallel to decrease the total resistance. The way I think of it is like this. If I give the charge more options for where to flow, it struggles less. Like it can pick different paths. So yeah, if I give something two rusty pipes to flow through that are side by side, the total ability of the thing to flow is still greater than if I just had one rusty pipe. It's got more options. So there's less resistance in parallel than there are for either individual resistor. Contrast that with series. In series, the equivalent resistance is always greater than R1 or R2 individually. The equivalent resistance is always greater than R1 or R2 individually because, you know, I'm kind of like stacking them. I'm stacking up my resistances. Something that's 2 feet tall and something that's 3 feet tall are both shorter than something that's 5 feet tall. Okay, I think that's all I really want to talk about for equivalent resistance, and I think we're getting a little close on time, so we will hit intuition builders and wrap up. Then, yeah, I'll end it there. Thanks, folks.